So good evening everyone and welcome to this 97th session of Saturday Talk by JanyuTech. Today we are privileged to have Dr. Aditya A as a speaker, and he is going to speak on the control robotics and the Bellman Equation. Aditya A received his BTech and MTech in aerospace engineering from the Indian Institute of Technology, that is IIT Bombay, in the year 2007, and PhD in aerospace engineering from the University of Illinois in the year 2011. He holds the position of senior scientist in Tata Consultancy Services (TCS) research. He is also honorary lecturer at Imperial College London and visiting associate professor at IIT Bombay. His research interests are centered around flight dynamics, control systems, and multi-agent systems. Apart from that, he is also on the advisory board of JanyuTech, and he has been guiding all our team working on the SATCOM project. Sir, over to you from here. Thank you so much.
Thank you very much for the invitation. So I've been working on and off with Janyu for a while now, so it's always a pleasure to attend these sessions, and then also today to get a chance to just share some of my thoughts with you. So what you're going to see now is not entirely my work, but it's a little bit of a perspective. So as an academic, one thing we always try and do is not just look at the state of the art, but also try and put it in a historical context. See where those ideas came about, look for common threads, because that is what helps you unify different fields. And then, of course, look for ways to bring ideas from different fields to our own native fields, and then, of course, go back in the opposite direction as well. So this talk, in some sense, is a result of that kind of a thought process. I hope you'll find it interesting. So I'm going to talk today mainly about the Bellman equation. And as you'll see, it is because the Bellman equation is now very much front and center in a lot of the work that happens on learning, and indeed also a lot on robotics. And I'll talk a little bit about that part towards the end as to why that has happened. And in doing so, I'll present a historical perspective, but we'll also come very soon to the state of the art. Now, for the rest of the talk, I suggest we just keep it informal. I'll walk through the slides. If you have any question, just ask me. The only thing that's happened now is because my screen I've switched to full screen here on my computer as well. I cannot see if anybody raises their hand. So please just feel free to stop me and ask questions. I may not be able to answer all of these questions since these are very deep waters, and there are areas that I'm aware of and some that I'm not. So where I'm not, I'll tell you as much and I'll direct you to the appropriate references. So with that, let's move along. So I think let me start by telling you a bit of the history of how controls and robotics have been doing for maybe the past 50 years or so. And with that, I hope you'll understand why the Bellman equation now is suddenly so front and center. In fact, more than the equation, I want to think of the Bellman equation as a way of thinking about problems, and that will become apparent very soon. So the history of control, specifically what we call optimal control, now really dates back to the 1940s with the work of von Neumann on what we now call as game theory. But that work really laid the foundations for what we also now call dynamic programming. But a lot of these ideas really started coming together in the 1950s. So 1956 was really a pivotal year because four major developments happened at that point, which had far-reaching impacts on not just how we solve control problems, but importantly, how we think about control problems. So the first that I've mentioned here, the Pontryagin principle and Bellman equation, relate very much to optimal control. So Pontryagin principle is a way to solve optimal control problems. And in some sense, it is not the same as the Bellman equation, but there are some overlaps, obviously, because they both try to solve the same problem. And both of these were published in 1956, to be precise, for the very first time. Now, for those of you who are interested in AI, would also know that this was the year in which the Dartmouth workshop took place, in which the field of AI was to some extent formally defined, as in people got together and defined what kind of problems or what kind of objectives would fall under the ambit of AI. So problems like planning, like perception, decision making, robotic path planning, these were formulated broadly as areas that would be of interest to the field of artificial intelligence. The last development that happened in 56, which is actually of a lot of interest to aerospace engineers in particular, is that of model reference adaptive control. So 50s was a time when combat airplanes started flying supersonic. The designs became more agile. As the wings became smaller and the planes started becoming unstable, handling the airplanes became a challenge for pilots. And so what was felt was you had to have a uniform set of handling standards, which actually came about in the 1940s itself in the form of what we now call handling qualities. But you also needed a control law or a control technique which could smooth out differences between different airplanes, between different flight regimes, and keep a uniform handling standard across the flight envelope. And that idea of uniformity was captured in this model reference or a reference model, and that gave rise to MRAC. And these things happened in 1956 itself. This was also a time when Rudolf Kalman was active as a researcher, and it was in 1960 and 1961 that he published his now legendary papers, 3 papers in fact, on there was a paper on what we call Kalman filters first, there was a paper on what we call Kalman-Bucy filters, and those Kalman-Bucy filters are in fact now called Kalman filters because they really differ in how you add measurement noise to the system. And another interesting development that happened was the development of linear quadratic regulators, or LQR. And I'll tell you in some time how LQR came about as a result of Kalman's attempt to prove something about the Kalman filter. So it's not like he was thinking of a control method, but he realized there's actually a way to prove how my filter works if I think of it as a control problem. And that gave rise to LQR. And I'll tell you about it in some time as well, because it's actually tied very closely to the Bellman equation. And that was a time when a lot of things that we now know about state space control, things like controllability of systems, stabilizability, these are all properties of state space systems which are essential for control. Those got formalized as a result of Kalman's work during that period. So in that sense, this period from, let's say, 1950s to early 60s was really quite formative for a lot of work, just on the basis of its own perception, its own detection of obstacles, and then computation of the route. And the A-star algorithm, as we'll soon see, was actually a direct attempt to solve the Bellman equation in the context of robotic planning problems. And when I say robotic planning, there's a specific reason why I'm using that phrase, which will hopefully become clear in some time as well. And then things sort of developments kept happening, but in the context of the Bellman equation again, the next major development was towards the end of the 1970s in the form of model predictive control. And this was a time when, of course, it was realized that the Bellman equation was universal, but a technique was needed if it had to be useful in industrial settings. The model predictive control as a family of methods came about from the oil and the refinery community as part of their attempt to formalize a planning process for whatever it is that they do in refineries. In fact, I have one example at the end of the presentation where I'll show you a little bit of model predictive control and some reinforcement learning as well to go with it. Thereafter, so this was still on the control side, and then two other developments happened. I'm sorry, I've actually got some of the order on the timeline. So work on AI, work on learning had been actively since 1965, but there was a question about how you go about implementing it in practice. And this work was important in the context of this lecture because, again, all of it was oriented towards solving the Bellman's equation in a very practical sort of way. And the idea of neural networks had existed even before the 80s, but it was with Jeff Hinton's work in 1986 when he put forth the back propagation algorithm and showed how it worked, that the idea of using deep neural networks actually became feasible. And I mean by feasible, I mean you had a formula now to tune weights, and it was one that was computationally tractable. It was literally a one-shot formula. You just applied it. There were no iterations needed. So if you had to visualize the operations, it was an acyclic graph, and that was perfect for implementation, for rapid implementation. That happened in 1986. And sure enough, in a couple of years, in 1988 to be precise, a paper was published showing that neural networks could approximate any kind of a function given a sufficient width and sufficient depth. So that was the universal function approximation theorem. So these two ideas, the universal approximation theorem and the backpropagation technique which Hinton developed, these two things together laid the foundation for what we now call deep learning. And the other ingredient for deep learning was this method called Q-learning, which finally gave rise to a computationally tractable way using simulators or real-world systems to actually solve Bellman's equation in a practical sort of way. So in that sense, some kind of a closure happened during that period. And from there on, it's these techniques that were developed, and they've developed into the field of reinforcement learning that we see now. And a couple of developments I want to mention. These happened in the mid-1990s. This was an attempt to build upon the work on A-star algorithm. Again, solve the Bellman equation in a very practical sort of way. And that gave rise to two families of algorithms in robotics. One's called PRM, or probabilistic road maps, which we will look at in a couple of slides from now. And the other was called RRT, or rapidly exploring random trees. And in some sense, with the work on PRM and RRT, a closure of sorts happened where Bellman's equation could now be solved with sufficient speed in a robotic setting. So what you see here on this slide is not just the story of how something that started as a set of ideas in the 50s evolved into concepts, but you also see some sort of closure happening at a conceptual and at a practical level. This is not to say that all problems have been solved, but when you have a closure, you can take that technique, take that idea, and take it to its logical end in a practical sort of setting. And that's what I actually hope to show you through this particular slide. So let's move on now to the Bellman equation. Now, the next few slides, I'm going to talk about the Bellman equation itself. Some of you are going to be familiar with it, and so I apologize to you if I end up repeating something that you obviously know. But for those of you who are not familiar with the equation, I thought I should at least tell you what it is at some length, and then we'll get into how it's actually how it's actually driven control and robotics and how it's actually solved in practice. So we'll keep life simple. We'll assume that everything is deterministic, and the setting is as follows. So you have a system that's evolving in time in an environment. At each instant, the environment and the system are described by some state S. This could be a function, could be a vector, could be anything. Now the system takes some action A, which modifies the state of the system and the environment. So you have this kind of transition in the system that a new state S prime depends on the current state, the current action, and could depend on a lot of other things, including a history of both S and A. And in response to this change, the system accrues a cost, the environment provides a reward. We call this a step reward. Think of this as a net reward that you get from the environment and something that the system may have wasted in taking this action, and that we denote compactly as this function R, which depends on S, A, and S prime. This is the setting, and this is very universal if you think about it. It occurs in engineering problems, but also in socio-technical problems. It also occurs in economics. So every time, let's say the RBI raises the interest rates, this is exactly what's happening. This is the state of the market. The interest rate is the action. It changes that action. Something changes in the market. It sees a reward. Markets go up, markets go down. There is creation of wealth or otherwise. And what you actually want to achieve in all of these things is to maximize what you accrue over a long period of time, and that is what's written at the bottom. So let's start from the very right. You sum rewards over a period of time from 0 to t. All right. You want to maximize this total reward. You don't care about the step reward. There are times when step rewards may not be great, but this entire reward has to be maximized. And if you're a policymaker, what you care about is not what this reward is going to look like, but what you care for is what actions you need to take to maximize this reward. And therefore we say argmax. We sometimes denote this reward compactly as J star, and what you want to solve for is the series of actions A star that are going to get you the highest possible reward. This is a problem that you want to solve in any kind of a practical setting as well. Again, to go back to that little example with the RBI, if RBI could, they would want to plan their sequence of interest rates for the next 5 years and bring some predictability into the market. In engineering, if a robot has to go from point A to point B, it's going to want to take actions that minimize energy loss and get it to that point in the minimal possible time. So it's the same set of problems that are being solved in all of these different disciplines. And you see how nicely it already starts looking like a very nice unifying framework. All right, so let's move on. We're not at the Bellman equation yet, but this is the setting for the Bellman equation. All right, now there are some nice ideas here that help you actually get to the Bellman equation. So let's look at just the cumulative reward now. Don't worry about the action just yet. Let's look at the reward that you get by taking some series of actions A from time 0 to t. Now, one key principle that was actually obtained not just by Bellman, but even by von Neumann before Bellman, but we call it Bellman's principle of optimality because he was the one who studied it in these terms. So suppose I have an optimal trajectory, which is shown in the plot on the right. Here, by the way, this state x sub 0 is, think about it as the net reward that you accrue over time. So that is what this state is. So don't worry about why we have a different notation. This figure's taken from a book where they introduced this as a new state. And here you have the state of the system x. Okay, S really is x here. You start in some initial state x0, and at time 0, obviously you've not done anything. So you've not accrued any reward. So the reward is 0. And here you have the optimal trajectory, which takes you to this terminal state x1 or this terminal surface S prime. Okay. And y star of t star is the description of the trajectory, including the reward. What Bellman's principle of optimality says is that any terminal segment of the optimal trajectory is itself optimal, treating the starting point as the initial condition. So what do we mean? So let's say we start with x0, we keep going, and we get to this particular point where you see these little two lines bifurcating. All right. Now, I claim that y star is an optimal policy. Okay, so it's going to give me the best possible reward x0. What Bellman's principle says is that it's not possible to find any other trajectory which can do better than x0. In this case, we are probably trying to minimize y star, so that's why it's this impossibility being below, right? Now, this is the principle of optimality, and we'll see very soon how it actually helps us get to the Bellman equation. But keep this in mind. So the way to think about it is, if I have an optimal trajectory, then between any 2 points on that trajectory solving the Bellman equation entails solving this equation for all possible states. Okay. So if you are thinking of this as a robotics engineer, thinking, okay, I have a robot starting at some point, I have a terminal state in mind, and I'm going to solve the Bellman equation in its most native form. Well, you're not going to solve for one initial condition. You're going to solve for every possible initial condition, and you're just going to cherry pick that one solution that applies to you. And that already shows you that maybe this is an expensive process. It's also an inefficient process to solve this equation. So what you will see from here on when we talk about robotics and control, is how methods evolve to solve this equation efficiently. In robotics particularly, initial conditions are typically known. You don't want to have to deal with every conceivable state. In control, the intractability is a problem, so you have to find ways to deal with this equation. So that's what I'm going to show you about control in robotics. And as I told you earlier, this is not just an equation, it's an idea, it's a concept, and it's had a significant impact on how these two fields evolved, starting in the late 50s. All right. Let's look at robotics now. I have a few slides on robotics, few slides on control, and then I'll wrap it up. So it's another maybe 10 slides to go approximately. Okay. So in robotics, one of the key problems that we deal with is that of motion planning. All right. And by the way, you will encounter both of these phrases, path planning and motion planning. The technical difference between these two is in path planning, you're only worried about the physical path, so X, Y, Z coordinates. In motion planning, it goes beyond X, Y, Z. It goes to the trajectory, and it really goes to every state that's of interest. So if it's an airplane or a satellite, even the rotational motion would be included in the motion planning. Whereas with path planning, you really don't care about those things. You don't want to solve for it. You just hope everything falls into place when you solve for the path. All right. The other important point I told you is that the initial point is usually specified. Right? And what that means is, remember we talked about an optimal policy. And I told you that when you derive the optimal policy, let's say even for a fixed terminal point, you're going to derive a policy that applies to every possible state, which means whatever you solve for has to be solved for every possible state. And you don't want to do it in a robotic setting. You don't have that kind of time. You don't have that kind of resources when using algorithms in real time. So you want to be able to solve something that looks like the Bellman equation, but you don't want all of the complexity that goes with solving for the entire state space. So what's happened in robotics eventually is that methods evolved which rely on some form of neighborhood sampling. So if you're at some point, let's say at the initial point here, you will sample the neighboring areas, you will see what cost it incurs to get to those points, and you will use a clever way to get some approximation for that cost to go. I'll show you exactly how that's done in A* in just a moment. So these methods, sampling-based methods, evolved in the field of robotics because of this whole idea of the initial point being more or less fixed. These are rarely used outside of robotics, by the way, but it's a nice way to solve the Bellman's equation. All right. And for those of you who work in robotics, I mean, I know Janyu has a significant portfolio here. One consideration is, well, do you want to separate path planning from motion planning or from trajectory planning? That's of interest because these methods I'm going to tell you about very soon evolved to solve the big problem with path and trajectory planning. But I'll show you examples where we separated these two. So we allowed trajectory planning to happen in a completely independent setup and path planning to happen in a completely independent setup. So path planning was being solved for using Bellman's equation, but for trajectories, we didn't do anything. We used a straightforward open loop stitching approach that you will soon see. All right. Now, I told you earlier about A*, and A* really evolved to solve Bellman's equation directly. So what you see in this sketch is A* in action. So let's just pause it for a minute if possible. Okay, it's not letting me pause one moment. All right. But what it's doing is this. Suppose you have a gridded world as shown in this video. All right. From every point, there are areas that you can get to. So those are the neighboring cells. There are some no-go areas which are black. Every hop comes at a price. In this kind of a world, that price is uniform. And you want to get from the starting point here to maybe the goal somewhere here in the minimal possible time. And you clearly see how this equation comes into being. The trouble is, when you start at a state S and take a hop, you don't know this guy because you don't know the value function at all in this case. All you know is R. So what A* did was to come up with something called as a heuristic. So those of you who've worked on A* know this guy, that we create a heuristic function that approximates G. And what you do is that as you take a step forward, you update the heuristic for the state that you've just traversed at every parent state of that state. So if, for example, after a few hops, I end up in one of these states, I update V* of that state, and using the same formula, I go back and update V* for every state that I've visited previously. And I keep doing this until I get to the goal state. And lo and behold, once I'm at the goal state, its own V* is 0. And because of the approach I've taken, I've actually been updating V* for every state. And that's it. I have V* now, and I know my optimal path as a result of it. And this was the first algorithm that was developed in 1965. And that robot I showed you earlier, Shaky, actually used this algorithm to traverse a gridded world. And so you see that the very first motion planning algorithm, the first systematic motion planning algorithm, actually came about as an approximate way to solve Bellman's equation. Now, as it happens, while A star is quite good, the idea that you have a gridded world can be a restriction. Our worlds are not gridded. I mean, yeah, we can have road maps, but our real world is not gridded. So that gave rise to the idea of what are called as probabilistic road maps. The idea was, how do you extend A star to continuous spaces? So the first step is to create a roadmap using sampling. That's where the probabilistic word comes in. And what you see in this figure here is how sampling happens. You sample points and you start connecting points to neighbors with some constraints. So for example, if you sample a new point, you put a restriction on the distance, you look for feasibility, and if it's feasible, you connect them via a road. And for each of these edges that you see in the graph, there's a cost of traversal. There could be additional constraints. But once you have created this particular roadmap, you can apply A star straight away, right? So this was the first technique that came about in the 1990s. It came from Lydia Kavraki and John Latham to solve for A star in continuous spaces. Now, the challenge with PRM, though, while it looks nice, is the following. When you create a roadmap of this sort, you've basically created a huge database of points. And if I were a robot starting from one point, if I had to get to another, solving A star on this roadmap can be really quite complicated. I mean, you can try it in practice. It's not easy. It's quite cumbersome in real-time conditions. If on the other hand, you have applications like Uber, where you go in a city where the roadmap exists, it's perfectly fine to use PRM. It's very powerful. But if you have a robot that's just asking you for a route between one point and another, it's a single query, no guarantees that such a thing will be used in the future, then PRM and indeed even A star are both an overkill. So that leads us to the next method known as RRT, or rapidly exploring random trees. It's a single query algorithm, which means you give it an initial condition once and for all, and you tell it where you want to go once and for all. It's going to sample the environment in real time. It's going to look for feasible connections, and it's going to build a very special graph. What you saw up until now was a generic graph. No, there was no structure to it. This guy builds a tree, which means that if my tree ends up on the goal node, all I have to do is start from that goal and go back down the tree. There are no cycles in trees. There's a single path from the goal to the initial condition, and that is it. It has been solved for. Nothing else remains to be done. So RRT has actually evolved into a fairly strong approach. It's very practicable as well. And in fact, it is the state of the art. So let me show you an example that comes from our own research. In fact, these examples are drawn from our work. We were able to, in fact, implement RRT on an online, on a computer which sat on an airplane. It was a Pixhawk board with a minimal computational architecture, and we were able to implement it. So let me see if I can play this video for you. One moment. It's going to probably need me to use my pointer. You can look at the kind of maneuvers the airplane is doing. These are very aggressive maneuvers. It's doing knife edges, it's doing hover to cruise, it's doing hammerhead turns, and it's been given a virtual map of the environment. And in real time, at the start of this maneuver, at the start of the maneuver sequence, it figured out where it wanted to go using RRT. Every time it sampled a point, it tried to construct a maneuver between the 2 points. Sometimes if it figured it had to go through a corridor, it knew that it had to use a knife edge. So it tried a knife edge. And accordingly, this whole path was built online and it was flown by this particular airplane. So you see, RRT is really quite powerful and it's quite practicable, as you can see from this one example. And the other thing I want to show you in this case is what happens when you use different methods for path planning and trajectory planning. If you look at these two plots here, what you will see is a blue path, which is the terminal path, the path that's actually flown by the airplane. But you see all these black segments. These are all points that are sampled by the algorithm, and it tries to create paths here. This is a maneuver space that we created. It also includes some aggressive maneuvers like knife edges or hammerhead turns for sharp turning. And what you see at the bottom are standard Dubin's curves. So these are straight lines and only sustained turns. And you just notice that once your maneuver space expands, if it's chosen wisely, you notice how little sampling is really needed. And that's what RRT is good at. RRT actually samples near the edge of your sampled envelope. It doesn't care about things close by unless a bad maneuver space forces it to look at things close by. So it's not so much that you just want to get rid of the motion planning part and make it a simpler problem in the form of path planning, but using your knowledge of physics or your domain knowledge, you can actually use these kind of nice design principles and simplify the planning problem as well. Okay, so what's the state of the art now? So as I told you, RRT and PRM came about in the mid to late 90s, so almost 25 years ago. But they are still very much state of the art because they really solve the Bellman's equation. They do it efficiently, and as of now, other than variants of PRM and RRT, or occasionally A star plus RRT, A star plus PRM, we do not have anything better than these algorithms at a fundamental level. So these are state of the art. And in fact, these are now available even as standard implementations. This is something called as the Open Motion Planning Library, developed by Lydia Kavraki's group itself. So Lydia Kavraki was the one who came up with PRM, and you can use it in ROS in any application that you have to. So moving to control now, the idea of control is the following. Suppose in robotics, you have this path plan that you've created and you solve for it. Well, control really refers to how you solve problems locally. How do you ensure that your trajectory is correctly regulated? So the path plan asks for a certain velocity, a certain angular rate, for example. Control deals with how best you deliver it. Now, the reason why I mentioned this is because although we talk about the Bellman equation, we talk about long-term problems. The way I've explained the control problem, it appears to be a relatively short-term problem, right? But despite this being a short-term problem, we still use something like Bellman's equation because Bellman's equation gives us a policy. So although control problems may have objectives that shift from point to point, my policy doesn't have to shift. So unlike the planning problems that you saw in robotics, where we didn't care for a policy, we cared for one specific solution. In control, we care for a policy, at least ideally. So in control, as I told you earlier, our typical goal is minimizing some tracking error, the difference between the output and some reference signal. So more often than not, what we care about is this thing called asymptotic tracking. So you start with whatever error you have initially, and as you see in this figure, you hope that it dies down gradually. In piloted flight, as the question earlier hinted, these characteristics become important, right? So you don't just want the error to die down, you want these transient characteristics to be chosen correctly. And the optimal control formulation that we've seen so far in terms of the reward does nothing to deal with the handling at all. But nevertheless, as I told you, when Kalman was working on Kalman filters, he realized that there was some reason why you might want to use LQR. And in fact, he devised it as a solution to a problem. So you have this kind of a quadratic cost here. So you have the same tracking error squared plus cost of the control input squared, right? And you want to minimize this quadratic cost. And typically these two terms are weighted against each other. So they're not exactly, the weights are not one as shown here. Now, the trouble with LQR is it only deals with linear systems and quadratic costs, and it gives you a solution by hand. Now, what happens if you don't have a linear system or your cost is not quadratic? You can still use an exact solution for very trivial cases, but generally it doesn't work. And that's when MPC was devised towards the end of the 70s by the oil and gas industry. So here's the idea. Okay, I want to solve an optimal control problem over a long period of time. I don't even have enough data about my system to solve that problem reliably. So I break it down. I create a short horizon problem. So in this case, it's shown as the prediction horizon from time k to time k plus n. I solve the optimal control problem only over this horizon. And in fact, in classic MPC, again, this works well because of the fact it comes from a specific industrial context. Your control inputs are just piecewise constant. So it becomes a search problem, not solving for arbitrary control inputs. If possible, you update information about the system. So if you have information from your sensors about the state of the system, about, for example, the temperature in your column distillation units, about pressure in certain areas, if something has failed, you can update it at the start of the prediction horizon and then compute this solution and let it run only for some time. So you don't run through the entire green patch. You run through a part of it, typically a third of it or a half of it, and then you repeat this process. And you keep going on ad infinitum. Now, what have you done? The first thing you've done is that you've made the problem computationally tractable. Okay, so instead of solving the Bellman equation over a long time horizon, you're solving it over very short time horizons instead. The second thing that you've done is that you've given yourself the ability to deal with uncertainties in the model. The trouble is Bellman equation requires that you know the model. I just told you that there is this function f which maps your current state to the future state. We never saw it in the Bellman equation, but you need to know it to solve the Bellman equation in some ways. It took away some of that pressure because it says, well, I only need short-term knowledge, which I can safely assume I have. I don't need to know what's happening in the long run. So it allowed your procedure to become adaptive in nature, right? That's what MPC achieved. And of course, MPC now is state of the art with one or more variants. But again, MPC still requires that you know the system, even if you need to know it for a short time horizon. What happens if that is not the case? If your system is only available to you, for example, as a black box simulator, and that's where reinforcement learning came in. So unlike LQR, where the system is linear, unlike MPC, where a system is known, you now want to solve general optimal control problems for poorly known systems, where analytical solutions don't exist, where heuristics don't work satisfactorily. So the idea now is that you solve this equation iteratively. You assume some form of V. We actually work with a special form known as the Q function, which also depends on the action. You parameterize it in terms of some numbers mu, and depending on how badly you are off, if you just look at the first Bellman's equation here and you look at what I've written here, you see that these equations look very much alike, except that there's an error involved here. So if I have this error all the time, it means I've not reached the solution to the Bellman's equation. I've reached something else. So you adjust the parameter mu. This is loosely what reinforcement learning does. There's a lot of extra detail in here which I've not gone into, but we don't even need to know that at this point. Right? So really reinforcement learning came about as a series of methods to simply solve the Bellman equation, right? Now it's a perfectly mature area. Okay, there are well-known toolboxes in control, including in RL. But what are the challenges there? These are all state of the art, by the way. As you just saw right now, you still have to develop good quality models if you have to apply any of these methods. Another challenge which we've not addressed yet is safe. And what is safe learning is a challenge. Transfer learning is being addressed. I wouldn't say this is it's an open problem, maybe not conceptually. Safe learning is still a relatively conceptual open problem. And the other problem that you have is on optimality. So you're trying to solve Bellman's equation, and what you hope is that any method you use actually gives you the solution to the Bellman equation, gives you the solution. But these methods very often don't do that. You don't know the system, so you're solving for an approximate solution. This is a plot from a paper which first introduced SAC, one of the methods. So it's called Soft Actor Critic. It wants to compare itself against 3 other methods. And you see 5 curves here. Okay? What is interesting, never mind which method outperforms which method, notice the difference in the performance, right? One method gives you a return around 300, 400 units. Some other methods able to do it over 5,000. When these methods came about, they were all state of the art. They are all trying to solve the same problem, but neither of them guarantees that it's actually solving the problem perfectly. And this is an inherent challenge in reinforcement learning. In this case, you see SAC outperforming everything. SAC here, the blue and the orange lines, outperform purple, which is PPO or proximal policy optimization. They outperform green, which is TD3. I don't remember what TD3 expands to. And it outperforms DDPG. Whereas in the previous example that I showed you from our work with the industry, in our example, DDPG did much better than SAC. So it tells you that there are risks inherent in applying RL. So you have to be a little cautious. Yeah, it's mature. There are toolboxes, but these guarantees on optimality don't still exist. So that's really an open problem right now. So a quick summary now. So you've seen now how the Bellman equation leads to a lot of the state of the art in controls and robotics. See, all of the problems that we've looked at are fundamentally planning problems. Planning over long horizon and control over short horizons, control with a policy. These are all fairly mature at this point, but there are challenges. I just showed you what happens because you can't prove optimality with some of these methods. There are also issues with real-time computation, and safety can actually be a substantial challenge because some of these methods don't by themselves guarantee safety. You have to build it in some other explicit manner. Now, I told you at the very outset, and I'll close with this, I'm mindful of the time. I told you at the outset that in control, we are used to thinking of policies as the way to go, but we are moving away from that. So what's happened now is that with computation becoming faster without actually adding weight to your processors, the thought process now shifted to, well, can we solve for the control actions in real time by solving iterative problems? So every time you solve, for example, a linear programming problem, even something as simple as an LP, it's iterative. If you try to describe the operations, you have to run some operations over and over again until convergence, right? There was a time when this was not possible, and that's why there was so much emphasis on control policies, but that has now shifted to the point where we can now genuinely do real-time computation on board. It's anybody's guess how effective it will be, whether the industry will absorb it at some point. At this point, we are not there, but this remains an open problem. And I thought I should talk to you about these because Janyu, I can see, is doing really well with robotics. You are developing great robots, but I think if you look at all of this technology, it's not just a way to solve existing problems. It's a way to actually take your robots to the next level. Each of these technologies would enable new problems to be solved. They allow multiple robots to work together. They allow robots to function efficiently. And I think this is where it would be great if the company now starts investing more time and more effort on absorbing these technologies. I'm pretty sure you're doing some of it already, but it would be great to see the company taking the role of a leader in developing this kind of technology as well. And of course, we are all here to help to the extent we can. So with that, let me stop. Thank you very much. I'm sorry that I overran by a minute. If you have any questions, be happy to take those.
Hi, Aditya. This is Arun. Quick question. You talked about reinforcement learning application in the oil and gas industry. Was there any attempt at digital twin modeling and then improvement of your RF?
Okay, that's a good question. So that particular engagement had a digital twin component. However, that's not what we developed RL for. So we had a very interesting situation. That digital twin for that refinery was available as a service from a complete third-party provider, and they weren't prepared to divulge what was in it. So they weren't even. So it's funny. So imagine a provider like ONGC. This project wasn't with ONGC. So somebody develops a simulation model for the ONGC refinery that's validated by ONGC. Now ONGC wants to optimize its operations, and they say, well, you can use that simulator, but nobody has access to what's in it. So yeah, we had a digital twin, but we didn't have access to what was in that digital twin, which is why RL became essential. All that we had a sense for what was the state space of. We had a sense for the state space of that digital twin, nothing else. In fact, what happens very often is people who develop digital twins at this point are maybe a slightly different community. They specialize in that domain, whereas people who do things like RL or control are people who specialize in those areas. And I mean, as somebody who works on flight control, I've had to straddle both of those, try to understand flight physics but also understand control. And so that obviously means we spend a little more time developing what are called as models for control. I didn't talk much about it, but more than a digital twin which has very high fidelity, what you really want is a model that does the best for control design. So for that refinery example that I showed you, yeah, we created a digital twin as well. I mean, we built one on our own for that example, which we needed to prove to our client that we had what it takes to solve the RL problem. So we built a DT. It also had things like crude blending built into it. But for control, we simplified a DT substantially. For instance, our DT had like a time tick of 15 minutes. So every 15 minutes you could update your decision. Whereas in our control DT, what we call the control DT, which we use for RL design, the time tick was 37 hours because that was one of the time windows in the system. So what you realize is that the digital twin that you need for an in-depth what-if analysis isn't going to work very well when you start doing control design. So you need some other model. You can call it a control DT if you like, because it's a relatively good representation of the system, but it is not of the same fidelity as a typical DT.
I think there's another question which reads, what are your views on the phrase state of the art? Why do we not call it as state of the science?
Yeah, I've never heard. I don't know. I never thought about it. Thanks. That's just a phrase that we've been using so far. But
when you say SOS, it means something else. That is a problem.
I don't know. I really don't. Actually, that's interesting. I need to see where that phrase came from in the first place. I don't know if you could just someone could just run a quick etymology check. We could find out where that phrase came from. But up until what is interesting is maybe until about 30s or 40s, engineering was still considered very much an art form. Control design for sure was an art. I can vouch for it. Even to this day, even with all the toolboxes, it is an art form. RL, despite all the toolboxes, is still an art because you still have to model things by hand to a great extent. So no, that art side hasn't gone away. And the reason why it's called art is because it is an expression of your own ingenuity. It's not something that a scientific principle is telling you about. It's something that's happening inside a black box that's telling you what you need to do next. And I think that's my take on it. I don't know how useful it is, but okay, I'll leave it at that. Okay, thank you very much.